Okay, we're back. So,
Hello.
the next speaker is Martin Wickham, also known as Specs Guy. So, please, Martin, introduce yourself. Oh, yeah.
Hey.
Thank you.
Hey, everybody. I'm glad to be here. I've been using Zig since about 2019, and I've been pretty involved in the design of the language, and so I'm really happy to see a lot of you in person, and I'd love to meet all of you. This is a fantastic conference, and thank you, Loris, for putting this on. This is amazing.
Thank you. Okay, I'm looking forward to listen to your talk, but first, I want to disarm one question that I fear the audience is going to ask you right after your talk is done. So I'm going to actually ask it now in everybody else's stead. So when is async coming back to Zig?
I am the wrong person to ask.
Yeah, so you heard
I have no idea.
Him. Okay, he doesn't know. It's not the right person to ask. Thank you. Okay, please, let's
Thank you. All right. Hello, everybody, and welcome to Foo Corp. As you know, this is new hire orientation. Thank you all for attending. It's been a long day, but this is our last session, so bear with me, and I think we'll have some fun. We're going to take a look at a bunch of real examples of Foo Corp code where we've had some problems with optimization, and we're going to talk about the simple problems in code that lead to very bad optimization and small changes you can make to make the optimization better. But first, we need to start with a few disclaimers. The first one is that we're not going to be talking about the actual compiler implementation. Instead, what we're going to be discussing, is a mental model for thinking about how the compiler thinks about your program. So we're gonna talk about some simple rules that you can emulate in your head to see where the compiler might run into problems. The second, if you really want to know what the compiler is definitely going to do, you need to run it, and you need to look at the output, and that's always very important when you have performance problems and when performance is important to you. The second thing is that most of the performance that you can get out of a program is not in the control of your optimizer. It's going to be based on your data layouts and your virtual function calls, and you really need to avoid those things and have very good caching behavior and very good memory behavior before these things become important. So once you've got like data-oriented design stuff and you've got very like solid foundations, then you can start using these techniques to squeeze the last bit of performance out of a higher level language. If you are interested in like how the compiler actually works and more info on that, there's this fantastic talk by Chandler Carruth called Understanding Compiler Optimization. I'll have this link up again at the end so you can take a picture of it. As you know, here at Foo Corp, we're known for our Foo Style API, our most popular product, and we've achieved market dominance in the field of Foo Style APIs because of our high quality BAS, which you can see we provide through this get BAS API point. So we have this get BAS function. We have a pretty standard C++ code base style. So we have this in a header, and then in foo.cpp, we have our implementation of get BAS, and this is just going to return BAS, of course, because it's a getter. And then we also provide, as a convenience API, this accumulate function, because often what our users want to do, of course, is add up all of the BAS from their foos. So we have this accumulate function, which is looping over a bunch of foos and calling get BAS on each. Now we have a standard compiler pipeline, so we pass each CPP file to a separate compiler instance, and then those go to the linker to produce an executable. Now, because these are compiling separately, they're also optimized separately. And so the optimizers working on each CPP file can't see any of the other CPP files in the project. And so the optimizer working on this accumulate function has to imagine what getBas might do, because it can't see the implementation. And so it's going to imagine something, and we can imagine that getBas might do some pretty terrible things. for example, it might walk up the stack and look at all the stack frames. And then, if I'm putting on my evil programmer hat, it might take the bytes of the stack frame and reverse them. And then maybe it'll use the debug information of the program to look up the range of instructions for the function, and then it can hash those and combine all those hashes together. And then we can cast away the const on this getter, on the this pointer, and write to the object that we're getting a field from. And then we could check if that hash is even or odd and use that to print something so the user knows whether or not that hash was even or odd. And this is pretty terrible because the optimizer needs to not change what the program does. Like, the program's supposed to do the same thing with the optimizer on or off. And if the program can do stuff like this, that's never going to work. Like, calling any function that the optimizer can't see basically prevents the optimizer from changing any instructions because, like, the hash would change and the user can see that because it prints, right? So we're going to need to set some ground rules as the optimizer. So the first is there are things you can write in the language that the optimizer can assume that the program is not going to do. Because, like, if you can do some of these things, it just completely destroys the ability of the optimizer to change anything about the program. If the program decides to do those things anyway, then the optimizer gives up its guarantee that it's not going to change what the program does. And finally, because the optimizer can do a lot of, like, non-trivial transformations, it can take things that aren't in the program and put them on the stack, for example, and, like, if you do something like reversing the stack bytes, it's hard to say what that'll do. If the way that the behavior changes could be difficult to predict. It's sort of like something's going to change, but even as the optimizer, it's hard to say exactly what that change is going to be. So you might recognize these rules. They have a name in C++. They're called undefined behavior, which is kind of a weird name for them because we haven't really been talking about defining anything. This is just kind of what you need in order to make an optimizer work at all. And I think undefined behavior is a difficult topic because a lot of people dislike it, and there are certainly pieces of undefined behavior in C++ that I think are poorly chosen. But you need something like it to make an optimizer, to give an optimizer the freedom to make changes to code, because you can observe all possible changes that the optimizer might make. So Zig has a much better name for this. Zig calls it illegal behavior. This is the things that the optimizer has decided are illegal. So let's look at another example. Here is a humble loop. This loop is somewhat interesting, but not really. We're going to loop 10 times. And inside that loop, we're going to count how many times we loop, and then we're going to print that out. And then we're also going to take a pointer, and we're going to increment that inside the loop. Now, this is obviously code that I think no one here would write. It's rather silly. This is, not up to Foo Corp standards. But after inlining a bunch of functions and deleting dead code, the optimizer can very easily end up with code that resembles this. For example, if you're incrementing some value in memory every time you call a function, and the optimizer inlines that function into a loop, now you have this case where you're incrementing a pointer every time through a loop. So if we think about how to optimize this, you can think about, we know how many times this loop is going to execute. We can just kind of merge all the operations into one and just increment the pointer by 10 and then print out 10. We don't need to count 10 times, certainly. But we need to make sure that this is not changing the behavior of the program. And the tricky thing about that is this part where we're writing to a pointer. We're reading and writing a pointer. And we need to make sure that reading and writing that pointer won't change the behavior of this loop. And in particular, the dangerous thing here might be, so like reading and writing this needs to not change x, for example. A particularly devious programmer might be able to call this function in such a way where they predict where x is going to be on the stack, and they set up the pointer to point to x. And then our loop is going to execute 5 times, which is, and then loop, when we print, the code on the left is going to print 5 and the code on the right is going to print 10. So that's not great. Similarly, they could make it point to loops, and then our loop executes 10 times, and loops gets incremented twice per iteration, and then it prints 20. And those are both insane things to happen. Like, we don't want the compiler to be hamstrung by that. In particular, we don't want the compiler to be hamstrung by that, because if it is, that means that things like X here in this loop can never be put into a register. They have to live on the stack, because somebody might be depending on them being there because they're going to memory snipe it. And so if we want the optimizer to move things into registers and to be able to change the stack, to move things off of the stack, then we need it to make no guarantees about what's on the stack. So the actual rule that compilers use, or at least something very similar to it, is based on memory regions. So the idea behind memory regions is if you have a variable like X, like this, it gets its own memory region. If you have a bigger like array, it gets its own memory region. Every local variable has its own unique memory region. Every global has its own memory region. And these memory regions are unique. They have a fundamental quality to them that makes them different from the other memory regions. If we have a struct, that's still one memory region. The whole struct, even if it has nested structs, even if the members are different types, it's still just one region. So if we take a pointer to a memory region, that pointer is tagged with the memory region that it originated from. And then we can offset that pointer to point anywhere else in the memory region and dereference it to access that data. And this is all fine. This is normal. This is part of how code works. You can even do that sometimes if the type is different. So for example, here in this struct, we could take the address of C in the struct and then go backwards and use that to find A. And that's fine because the programmer knows how far apart C and A are. But the programmer doesn't know how far apart S and Y are, so you can't do this, like try to use S to go find Y and mess with it. And the compiler is going to use this as a way to think about whether certain writes or reads from memory could be related to each other. And this is what's going to allow or inhibit most of the optimizations that the compiler wants to make. Now, this term is this phenomenon where pointers remember their origins is often called pointer provenance. Provenance is a very old word that means where something came from. It's pretty archaic. People also sometimes refer to this as pointer providence, which is and while it's tempting to call out to a higher power when working with compilers, that is unfortunately not the term. So going back to the loop, if we look at this, we start with our pointer coming in. And our pointer is attached to some memory region, but we don't know what it is because it was created before this code ran. And we're trying to optimize this function in isolation. Then we have loops. That gets its own memory region. And then we have X, which gets its own memory region. And finally, we can look at our pointer write. And because neither loops nor X existed when the pointer was created, we can say definitively that the pointer cannot point to those regions, and therefore we know that writing to this pointer is not going to modify loops and it's not going to modify X. And so this is the way the compiler thinks about whether a write to a pointer is going to affect pieces of memory. And so can we make this optimization? Yes, well, maybe. Remember that everything we're talking about in this talk is an approximation. And if you want to know the real truth, you have to go look at the disassembly every time. In practice, the answer here is yes. I've tested on all three major compilers, and they do all make this optimization, which is good. So let's modify this example again. This time we've added a num parameter, and the num parameter is an integer by value, and instead of looping 10 times, we're going to loop num times. And we'd like to make the same sort of optimization, where we add to the pointer, and we print just the number. Show of hands, who thinks the optimizer can still make this optimization? Few people. Who thinks it can't? Most of the people. Interesting. No, it still should be able to by the rules that we've talked about, at least. I haven't tested this one, but the trick here is that num is also in its own memory region. Oh, you're absolutely right. Well, that's certainly an issue. Let's say it's a uint. At least by memory aliasing rules, this is fine. Thank you. But yes. So we at least know that writing to this pointer will not modify num. If we look at one more example, we've now made num a reference. Now, anybody think the compiler can optimize this? Nobody. Good. You guys are on the ball. So now the pointer could point to num. It could point, or num and pointer could be the same memory because they were both created outside of the scope of what this function can see. And so a caller could call it like this. That would make them the same pointer, and that would mean that this optimization doesn't work. What if we make it const? And of course, we're still assuming that this is a uint. If this is const, anyone think it can optimize it now? Nobody. Good. Okay. No. So const here does nothing. Const is mostly ignored as an annotation on pointers by the optimizer. It's because all it means is that the value can't be modified through num. It doesn't mean that the value cannot change. And it seems like everybody already knows this, so I'm going to go quickly through this. And so we can still have this issue where they're pointing to the same thing, and that'll still compile. It's still fine, but we will observe the modifications. Okay, let's look at another example. Here we have this string view. It's a length and a pointer. And we're going to have two extern functions. One is getDescription, which is going to take a pointer to that string view and fill it in with the description of our library. The other one is isSpecial. That's going to check whether a character is a special character that needs extra considerations for rendering. We can run this. We can write this reasonable isSimpleDescription function, which has a local string view description. It's going to call getDescription on it, pass in the description. And if that fails, it's failure. And then it's going to go through each character in this description string, and it's going to check whether that's a special character. This is pretty standard code that you might expect for checking, whether something is in a view. So ideally, we'd like the optimizer to optimize this loop to take the length and pointer fields out of this struct and put them into registers so that it's just keeping this register pointer that it's incrementing each time and it's going up to the length and we don't need to have we don't need to reload these values out of the struct on the stack every time. We want to get these off the stack so that our code can run more quickly. Let's see. So we have the length being pulled out of the loop into a register, and we want the pointer also being pulled out of the loop into a register. Now, this can't be done because the optimizer, remember, can't see the definitions of getDescription or isSpecial. And so when it runs, it's going to need to imagine what those might do. It needs to imagine the worst case thing that they could do, and it needs to make sure the program still works in that case. And in this case, the worst thing that could happen is that there's a global somewhere, which is a pointer to a string view. And getDescription is going to take the pointer that you pass to it and store it into that global. And then when you call isSpecial, it's going to write into that global and modify the data. And so when you're executing this loop, when you call getDescription, the compiler has to assume that the string view description is now known to other parts of the program and that they can talk about it and modify it and do whatever they need to it. And then when you use it later, whenever you call is special, even though is special is not being passed the string view, the compiler still needs to assume that it knows about it because string view has escaped from analysis. So get description, where we're passing the string view out of the optimizer's visibility, is called an escape, and later calls to opaque functions that the optimizer can't see are called clobbers, because they prevent the compiler from retaining intermediate values that it might know about because things might be modified. So we can fix this by changing getDescription to return a string view by value, and now string view is not escaping from the loop. And in this case, the compiler can maybe optimize this. So we're going to look at one more example. Now, at FooCorp, we always need to take great consideration for the business needs, and our food terminal only supports 32 characters wide. And so we need to make sure that we're not rendering any descriptions that are longer than 32 characters. So we have this clamp max function in our standard library, and clamp max is going to take a value to clamp by reference and a maximum value to clamp it to. And so we're going to pass in the length of our string view and clamp it to up to 32 so that we know now that it's not greater than 32. Now, we know that this is going to escape the length of desc, right? So certainly we can't optimize this length value into a register. Anyone think we can optimize the pointer? A couple people? Unfortunately, we can't, because remember, a struct is one memory region. And so, for example, an implementation of clamp max, as far as the compiler is concerned, might take the address you pass it, use the equivalent of field parent pointer to get the address of a string view, and then store that in a global, and then when you call is special, it can modify the pointer. And that's all fine. Like, according to the rules of C++, that's well-defined, and it works. And so the compiler has to make sure that it's continuing to support that code that should work, in case that's the code that's running. And so this is pretty annoying, right? But unfortunately, that's the reality of references. If you escape any part of a memory region, it escapes the entire memory region. Okay, so now we can get to the rules for how to play escapes and clobbers. Local variables start out not initially escaped. They are known entirely to the optimizer. If you pass a pointer or reference into an opaque function, that escapes it. This can also sometimes happen if you write it to memory that the optimizer is not tracking. If you escape any part of a memory region, it escapes the entire region, just like we saw in the last example. If you call an opaque function, like a function that the optimizer can't see or that it just decides not to inline and doesn't know much about, that clobbers all escaped regions, and the optimizer is then going to have to reload any cached values out of those regions, and it's going to need to make sure to store any modified values back to them before the call occurs. And then finally, as we saw in our very first example, pointers which are loaded from memory or returned from an opaque function or passed in as parameters are untracked. The optimizer doesn't know anything about what memory region these pointers correspond to. And if you write through an untracked pointer, that can also clobber regions that were escaped before the pointer was created, because the optimizer doesn't know that those are different regions. It thinks they must be the same. Okay, finally, let's look at one more example. Our new API here at FooCorp is our flib-flobber API. We've been working on this for a while. We're very proud of it. Flib-flobbers, as you know, are a very general problem. And so we have a base class here with a virtual function flib-flop. We also, for convenience, offer a flib list, which is a list of flib-flobbers. This is a list of items, and really it's a list of pointers to flib-flobbers, because since this is a virtual class, we don't know how big it's going to be. Then we also provide this function flobAll, which takes a flib list, and it's going to go through all of the items in the flib list and call flip-flop on them. Now, we're passing flib list as a pointer here. Does anyone see the aliasing issue, the escape clobber issue in this code? Okay, so what's happening is when we call flip-flop here, this is a virtual function, and the compiler doesn't know what this might do. So this is a clobber. The list pointer is escaped because it's passed in as a parameter. And so when we read list.num and list.items in the loop, these values are going to have to be reloaded every iteration of the loop. And this is all because flip-flopper is virtual. Now, since we're talking about performance, though, let's actually analyze the performance of this loop. So we're making a virtual call here. So the first thing it's going to need to do is fetch the vtable from the object. Now, that's probably going to be a cache miss because we don't flob all the time. This is something that happens somewhat rarely or maybe once a frame. So that's going to be 200 cycles for a cache miss, and that's per item because this is a list of pointers, and they're all randomly distributed in memory. Then we need to fetch the function from the vtable, and that's going to be 200 cycles. This time, this is probably only paid per type, not per object, because you have the big penalty once for every time you hit a new type, but then that type is in the cache the next time you hit it during the loop. So that's just per type. Then we need to actually jump to the function. Now, the function code is also in memory in somewhere, and so that's another cache miss. Well, it's a branch mispredict first, because we don't know where we're going to jump to. Each instance in this list can be different. That's 20 cycles per object, and then we have 200 cycles to load the instructions from our cache miss, and that's per type again, because each type uses the same function. Okay, finally, we have this hazard we've been looking at, reloading the list.num. That's probably going to be in the L2 cache because we have this list around, at least if we're thinking per iteration. And so that's going to be maybe 12 cycles for an L2 cache miss. But there's a trick here because this value is only used on the backwards branch of the loop, which is going to be predicted by the computer. And so when that backwards branch is predicted, it's going to start executing the next iteration immediately before this load is finished. And so it's going to start working on fetching the vtable for the next object without even waiting for this. And so this 12 seconds doesn't actually even manifest per loop. This only manifests on the very last loop when the branch mispredicts and it thinks it's going to loop again, but it doesn't, and it doesn't find out until 12 cycles later because it had to wait for the memory load to finish before it could finish evaluating the branch condition. And so this is 12 cycles total, not 12 cycles per loop. And suddenly this is seeming very small. Now, similarly, we need to reload list.items. This one is on the critical path. Again, it's going to be 12 cycles, but it's going to be like right there. You need to do this in order to start fetching the vtable. So that one is 12 cycles per object. So if we compute our total performance, let's say we have 100 objects of 5 different types, and we want to compute that. That comes out to about 25,000 cycles. And of course, this is all back of the napkin, and none of this is precise. There are other problems and stalls here, and you have to measure these things, but the orders of magnitude are approximately correct here. So that's about 25,000 cycles. If we calculate the benefits of our optimization, that's like 1,200 cycles, and so as a percentage, that's like 5%. And 5% wins in a slow program are nothing to sneeze at, but remember, this is not including the cost of the flip-flopping itself. This is only the cost of having a loop at all. And so this is a tiny optimization, and this is to the point that it's not worth doing. If instead we were to take our time and focus on getting rid of that virtual function, for example, if we could unify all of the flip-flop implementations into one function that maybe does some branching, Now we don't have to fetch the vtable from the object. We do still probably need to fetch the object because it's going to have some data in it we need. So that's 200 cycles per item still. We don't need to fetch the function from the vtable though. That code is just gone. When we jump to the function, we're not going to branch mispredict anymore. And then we're still paying 200 cycles. But the function's going to do some branching internally probably, so we do need to bring that cost back. We're still paying 200 cycles per type, but that 200 cycles is going to be it's not per type anymore. It's just 200 cycles total. And now when we analyze the performance of this, the optimization starts to look a little more attractive. So if we, again, say we have 100 objects of 5 types. We can also, now that our flip-floppers are the same size, combine them all into a flat array. And that removes our per item from fetching the object, because now once you fetch the first one, the rest of them are going to be prefetched into cache, ideally. And so that's going to make it much cheaper to iterate through all of them. So now when we analyze our performance, say we have, again, 100 objects of 5 types, we get about 3,600 cycles total for the loop. And if we compare that to our old value, this is an 85% performance improvement over the previous version of the loop with the virtual function. So that's massive. And this is like the first thing to optimize if performance is important to you. Like, completely ignore everything we've talked about in this talk. Go do that first. That's what's important. But once you've done that, now when we look at our optimization, we're saving 1,200 cycles on 3,600 cycles. That's about a third, and that's not bad. So once you've gotten all of the data cache and the instruction cache misses and your virtual function problems out of the way, these things start to become more important. There's a famous quote that is often misused, that premature optimization is the root of all evil. And this is from Donald Knuth, and he goes on to say that we should ignore small inefficiencies, except in the very small parts of your code that need them. This has been misused to say that we should ignore inefficiency, which is of course wrong, but the small in the quote is load-bearing. You should ignore these tiny inefficiencies, except in the very small parts of your code that need it. But in those parts, taking list here and copying the num and items explicitly into locals will save 33% of the execution time of the overhead of this loop, not including the actual flip-flopping. Inlining flip-flop might save even more, and maybe the compiler will do that for you, maybe it won't. Thank you all. Welcome to FooCorp. Sorry, please. You get it. Okay, so before we get to questions, please raise your hand if you have questions, and the mic will come out. I want to make some recommendations for further reading if you're interested in this stuff. First of all, if you haven't read the quote that the paper that the premature optimization quote comes from, please do. It's incredible, and it's not about what you think it is. It's an absolutely amazing paper that's very relevant to this talk, surprisingly. So that's structured programming with go-to statements. Then the talk that I mentioned earlier about understanding compiler optimization from Chandler Carruth, that goes into how the optimizer actually works and talks about the intermediate representations of the compiler and the steps in the optimization process. There's this other talk, Tuning C++, also from Chandler Carruth, where he talks more about escapes and clobbers, and he shows you how to write escape and clobber functions that will execute in your micro benchmarks. And so you can use those to control the memory behavior of your micro benchmarks without actually profiling, jumping into another C++ file and doing nothing. finally, this talk from Ofek Shilon on LLVM optimization remarks. LLVM optimization remarks is a tool in LLVM where the compiler will tell you why it couldn't perform optimizations on your code, and it'll mark up your code with like, hey, I wanted to move this value into a register here, but I couldn't because you're writing to this pointer later, and those two things are interconnected. So that can be a very useful tool. Thank you.
Okay, so thank you very much, Martin. I think so. You wanted questions that you wanted to end your talk afterwards, like where you're like branch predicting.
Exactly. Yeah.
Okay. So thank you very much. Let's have questions while August finds the next question. Your talk gave me a great idea. I think that's actually where you were trying to say that. So if you have a piece of code that you own that it's slow, if you convince somebody else who's part of the same general stack to introduce slowness that's like an order of magnitude worse than yours, now yours becomes a 0.1 optimization, right? Which shouldn't even be bothered to be done. It's a great idea, I think.
Yeah. If we just slow all the code down in the world, then we don't have to optimize anymore.
Right.
I think this is
just find somebody else that can do even worse, right? Okay, thank you. Let's go.
For the first example, does it help to add no alias hints to the parameters to basically do the work that the optimizer was trying to do, or at least bring it back?
Yes. You mean this example, or the first the loop example?
Yeah, for the loop example, one where
the one with the reference.
Yeah, and it takes num by reference.
Yes. If you have a no alias attribute, then the compiler is going to assume that the pointer points to a unique memory region that doesn't alias any of the other memory regions you use in the function.
That would help it optimize.
Yeah, so that would help it optimize, but you need to be careful because if you actually do want aliasing to be enabled, then it's going to optimize too much.
Okay, so one of the fun things that I've been watching from the sidelines is all the stuff they're doing to optimize Mojo, which a lot of it relates to looking at the LLVM inliner. And so my general question is, how often do you think this really comes up in practice versus the inliner just magically makes it go away?
So I think in real C++ code bases, you have a lot of problems with calling functions in other compilation units that prevent this from going away. I don't have a lot of experience in code bases where most of the code is in one compilation unit. I do know that LLVM will, even when it doesn't inline, it will propagate some information out of functions that it can see that helps it with this analysis, but I don't know the details on exactly what information that is.
Yeah, without LTO, it won't propagate that much also, so it's still a cogen unit limit. But yeah, in Rock's LLVM-IR, I've seen a lot of fun attributes that are just automatically there because of LLVM.
Yeah, exactly.
Any more questions? Let's do one or two.
Can LTO defeating the optimizer?
Yes, sort of. So what LTO is basically is you run the compiler front end on all of your source files, and then you put those together into one giant compilation unit, and you optimize that. Which, I mean, on the one hand, it solves the problem of the optimizer not being able to see into your functions, but on the other hand, you give up being able to run your optimizer in parallel, which for a large code base could be a huge problem.
Let's do one last question. I think there was one up there. No? No more hands? Maybe Oh, there's one.
In the example you had also, if the type is different of the pointer, also shouldn't it can assume that there is no overlap, right?
Yes,
if you
sort of.
Do uint an int, it would assume that.
Oh, you're right. Yeah, if it was a uint and an int because of a rule that we didn't talk about called strict aliasing, it would assume that they can't alias each other. If they were both uints, though, then you have the same problem.
Okay, I think that was it then. Please give it up for Martin.